Suppose we have a scenario where a force F is being acted on an object of mass m naught as seen in some frame S. Now, unlike in Newtonian mechanics, where force seen from one inertial frame, say S, and from another inertial frame S prime is same, the force seen being acted on the object is same. In relativistic mechanics, this is not the case. The force being acted on the object as seen by an observer in S frame is F, then force being acted on the same object as seen from some other inertial frame S prime, which is moving with some relative velocity v with respect to S, may be different. It may be something like F prime, and in general, F prime is of course not equal to F. So, how are these two forces related? That is, if we know the force vector as seen in frame S, how can we find the force vector as seen by an observer in some other frame, some other inertial frame S prime? So this is the objective of this video. But before we do that, we will discuss some prerequisite concepts that will lead us to the concept of what is called four force, and the three force, that is the ordinary force vector that we are familiar with in three dimensions, that will be just three components of this four force, these three components of this four force, and first component will be something else that we will see what it really is. So to go up to this four force, we need to understand what is proper time, then we need to understand what is four velocity. Before that, we need to understand what a general four vector is, and four velocity is a kind of a four vector. So we need to understand what a four vector is. Then we need to understand four momentum. Then from momentum comes the idea of four force. So let's go in this chronology, first starting with proper time. So suppose we have some particle of mass m naught moving in some general trajectory, and at some time t with respect to some frame S, its position is x, y, z. Now at this point we can associate an infinitesimal proper time interval d tau, which is related to coordinate time interval delta t, dt, as 1 minus, if u of t is the velocity, instantaneous velocity of the particle, then this is related as this, and which we can also write as dt by gamma u, where gamma u we define as 1 by under root 1 minus u square by c square. So this d tau is nothing but infinitesimal proper time elapsed in the proper time elapsed, which is the time elapsed in the clock of the particle itself. So this is actually the time elapsed in the frame which is moving with the particle itself. So this proper time is always lesser than the coordinate time. Now this was with respect to frame S. We could have some other frame S prime moving with this relative velocity v, and in that frame we could write the same proper time at the same event as dt prime by gamma u dash, where now gamma u dash is 1 by 1 minus u dash square by c square, where u dash is the speed of the particle with respect to this S dash frame, right? So like that we can take a series of reference frames S prime, S double prime, S triple prime, and at a particular point on the particle's trajectory we can write the infinitesimal proper time interval differential as this for each reference frame. So this is for reference frame S, this is for S prime, this is for S double prime, and so on. So this is an important relation to keep in mind. To know more about what proper time is, I have another video exactly on this proper time, so you can watch that. And now before moving to 4 vector, let's emphasize the fact that here this proper time interval is invariant from frame to frame. That is, as we transform from one frame to other frame, the proper time interval remains invariant. It doesn't change. The corresponding coordinate time interval changes, the corresponding gamma changes, which depends on particle's velocity, but the ratio of the two, which is proper time interval differential, it remains invariant. So it is a Lorentz invariant, we call it. So we call it, in other words, d tau is Lorentz invariant. Now let's move to 4 velocity. Before that, let's talk about 4 vector. What is a 4 vector? So we know for a typical case in which we have 2 frames S and S prime is moving along the direction of one axis with relative speed v. The relation between the coordinates of an event, say A, as written in S frame T x y z, and as written in S prime frame T prime x prime y prime z prime, is given by Lorentz transformations. So if you know the coordinates of the event in one frame, you can write the corresponding coordinates with respect to the other frame. So the Lorentz transformation are given by this set of relations. So x prime is your x minus vt by under root 1 minus v square by c square, and y prime, since there is no motion of the relative motion of the frames along y and z, so y prime is going to be y and z prime is going to be z, and your t prime comes out to be t minus v x by c square whole divided by 1 minus v square by c square. Now if we define gamma v as 1 by under root 1 minus v square by c square, then we can simply write this thing as gamma v times x minus vt, and this we can write as gamma v times t minus vx by c square. Now this set of Lorentz transformations we can also write in terms of a matrix relation. So if we take a column vector here and a column vector here, and we write here t prime x prime y prime z prime, and we multiply the first component by c. This is for the S prime frame. The corresponding coordinates for the S frame are ct, x, y, and z. So the matrix for the Lorentz transformation comes out to be something like this. So we have gamma v here minus gamma v beta 0 0 minus gamma v beta gamma v 0 0 0 0 1 0 0 0 0 1. Here beta is v by c and gamma v is 1 by under root 1 minus v square by c square. This is nothing but the same Lorentz transformation relations written in terms of a matrix multiplication relation. You can just do this matrix multiplication to verify that this and this are basically the same thing. Now we can introduce the concept of a 4 vector. So this is some set of 4 quantities which are transforming according to this matrix. So we actually call this a 4 position vector, we can call it. So this is a 4 vector. So we can define a 4 vector as a set of 4 quantities which transforms according to Lorentz transformation, that is according to this matrix. So if we write this as x is equal to some matrix, say L for Lorentz transformation, this is x prime, this is x. So any set of any column vector, any set of four quantities which transform according to this equation is qualified as a four vector. This is the definition of the four vector. So if you have a set of, say, set of four quantities a0, a1, a2, a3, and you are looking at this quantity in two frames, in one frame S and in another inertial frame S prime, then suppose these are the quantities in prime frame, and the corresponding column vector in the unprimed frame is this. Then if this vector is related, if these vectors are related by the same matrix, namely we have gamma here minus gamma v beta here, 0 0, minus gamma v beta, gamma v 0 0 0 0 1 0 0 0 0 1. So this is the same L matrix. So we can write it as, say, A is equal to L, A prime is equal to A L A. So we'll say that A qualifies as a four vector. So four vector is any set of four quantities which transforms according to Lorentz transformation. So that is to be kept in mind. So maybe we can write it, a four vector is any set of four quantities which transform according to Lorentz transformation. Now from here we can move on to the concept of four velocity. Actually there is more to four vectors, like the norm of the four vector, and which is invariant, Lorentz invariant. We can also talk about that. So from frame to frame, this components of four vector change, but there is something called norm of the four vector which remains invariant. So actually norm of the four vector is defined as, so if we have a four vector A given as A0, A1, A2, A3 in S frame, and the same four vector is given in S prime frame as A prime is equal to A0 prime, A1 prime, A2 prime, A3 prime, then the norm of the four vector A dot A is defined as, actually this will be the norm squared. This is defined as A0 squared minus a1 squared minus a2 squared minus a3 squared. And if you find the norm in another frame, that will be a0 prime squared minus a1 prime squared minus a2 prime squared minus a3 prime squared, and the norm remains invariant. That means a dot a will be a prime dot a prime, which will mean that this quantity will be equal to this quantity right here. Here this is similar to the way we take the magnitude of a ordinary vector in a R3 Euclidean space. This is similar, but here the norm is taken differently because the way distances are measured is different. So let's not talk more about that. Let's move to for velocity. So for velocity, so suppose we have a particle which is moving with some speed with respect to some frame s, with some velocity it is moving, and at some instant t it is at some location x, y, z, and at some infinitesimally later time delta t it is at some another location x plus dx, y plus dy, z plus dz. So we know that let's multiply this this first component by c. So c here and c here, we are just making the units of the time component, dimensions of the time component same as the length. So we know that this 4 vector transforms as according to Lorentz transformation, right? So this is a 4 vector. This is a 4 vector. This is the same matrix L that we had, and this is also a 4 vector, right? This is also a 4 vector, right? So if this is a 4 vector and this is a 4 vector, then if we take their difference, which comes out to be c dt dx dy dz, then this will also be a 4 vector. If you add two 4 vectors, it is a 4 vector. If we subtract two 4 vectors, it is a 4 vector, right? So this is also a 4 vector. Now we can construct another 4 vector by multiplying some scalar. So if we multiply some scalar, say lambda, then lambda times c dt dx dy dz, this is also a 4 vector, because lambda is just a number which doesn't change from frame to frame, so it is actually invariant. So this still remains a 4 vector. Now if we choose lambda to be 1 by d tau, that's a valid choice, because d tau is something which is also invariant. D tau is the proper time interval, and this is an invariant, as we have seen at the very starting of this lecture, that d tau was invariant. It was the ratio of the coordinate time interval and the gamma for that particular coordinate system. The coordinate time interval and the gamma change from frame to frame, but their ratio remains same, which is the proper time interval. So this is a valid scalar that we can multiply to this 4 vector. So this will make this thing as c dt by d tau dx by d tau dy by d tau and dz by d tau. Now this is also a 4 vector. Now this particular 4 vector, let us define by a symbol u, and let us call it for velocity. So for velocity is what? It is the derivative of the position 4 vector ct x y z with respect to the proper time tau, right? Now we know that that the relation between proper time d tau, proper time interval d tau, and the coordinate time dt is that proper time interval d tau is equal to dt by gamma u, where u is the speed of the particle. So if we substitute this thing into this 4 vector, then our u becomes basically c times gamma u this is dt by dt, and this will be gamma u times dx by dt, gamma u times dy by dt, and gamma u times dz by dt. Now this thing becomes your 1, and this is nothing but x component of the spatial velocity, this is y component of spatial velocity, this is the z component of spatial velocity with respect to, all written with respect to frame s. So we can rewrite these things as c gamma u, this is gamma u vx, gamma u vy, gamma u vz. So these are the components of my spatial velocity, right? So this particular quantity is called Four velocity. Now we can move on to defining four momentum. So for momentum, so we define for momentum of a particle with four velocity u and mass m naught as for momentum, let's denoted by capital P, is equal to mass times the four velocity. So if we substitute the four velocity here, that's going to be gamma u c, gamma u vx, gamma u vy, gamma u vz, where u is nothing but the speed of the particle, that is the mod of the velocity vector, and this we are talking with respect to some frame s. Now if we take m naught inside, we have this thing as gamma u m naught c, gamma u m naught vx, gamma u m naught vy, gamma u m naught vz. This is the four vector, that is the four momentum of the particle. So this is your four momentum. Now if we focus on the first component, gamma u times m naught c, this looks something familiar. From another analysis, we can prove that the total energy of the particle, total energy of the free particle is nothing but m naught c square by 1 minus u square by c square, where u is the speed of the particle, which is nothing but gamma u times m naught c square. As you can see, this quantity and this quantity look similar. They differ by a factor c. Actually, this quantity, as you can compare, is nothing but this quantity E divided by c, right? So this four momentum can be rewritten as can be rewritten as the first component becomes the total energy of the particle E divided by C times gamma u m naught Vx, gamma u m naught Vy, gamma u m naught Vz. Right? This is a really nice simplification. Now this quantity, let's call it Px, this let's call it Py, let's call it Pz. So these three components are the momentum of the particle. So first component of the four momentum tells you about the total energy of the particle, and the remaining three components tell you about the linear momentum of the particle. So this can also be taken as definition of linear momentum, where linear momentum vector P is nothing but gamma u times m naught v. Actually, let's call it u to be consistent. So since we are denoting particles velocity by u not v, let's call it ux, uy, uz. ux, ux, uy, uz, and similarly here ux, uy, uz. ux, uy, uz. Okay, so this is your three momentum, so called, of the particle. Okay, so the first component gives the energy divided by c, and the remaining three components give the linear momentum of the particle. So this is your for momentum. Now similarly we can proceed to for force, right? So we have this for momentum, and if we take the derivative of this for momentum with respect to proper time tau, then that becomes 1 by c dE by d tau and dpx by d tau, dpy by d tau, dpz by d tau. So we have something like this. Now again, we can use this relation between proper time interval and the coordinate time interval. D tau is equal to dt by gamma u. So if we substitute that in here, we get this to be equal to 1 by c gamma u dE by dt gamma u dpx by dt gamma u dpy by dt gamma u dpz by dt, and this we can write as gamma u by c dE by dt, and gamma u, this thing is your fx, this is fy, this is fz, so you can write as fx gamma u fy gamma u fz. So this particular thing is your this particular thing is your force, okay, so-called force, whose first component gives you rate of change of energy, and the remaining three components gives you the 4 vector. These components give you gamma u f, and this component gives you rate of change of energy, rate of change of total energy of the particle, right? So we wanted to see how the force transforms when we move from one frame to other frame. So if with respect to frame S, the force vector is F, and we move to some other frame S prime, in which the observer sees the same force as F prime vector, then how are these two related? If you know vector F, how you can find vector F prime? So now we seem to be getting somewhere, because vector F appears as these three components of a much more general quantity called force. And we know that force, since it is a 4 vector, it transforms according to the standard Lorentz transformation, which we can describe as like this, right? So now we can perform the transformation, right? So suppose we are going from some frame S to S prime. So we have the 4 vector in, this is the transformation matrix. We have the 4 vector in the primed frame, so we have gamma u dash by c dE dash by dt dash gamma u dash fx dash gamma u dash fy dash gamma u dash fz dash. We have this, and we have the Lorentz transformation matrix here, which goes like gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. And here we have the components of 4 4s in S frame. So this is in S prime frame, and this is in S frame. This is gamma u by c dE by dt is gamma u fx, gamma u fy, gamma u fz. Remember, this u prime is the speed of the particle in S prime frame, and u is the speed of the particle in S frame. So if you know in one frame, of course, by velocity transformation, you can find in another frame. So remember to also put primes on all the u's that you have in the components of the 4 vector, right? Now we can multiply and get all the primed components in terms of the unprimed components. So since we are only in this lecture concerned with the transformation of force, let's not talk about this first component, although we can do that, it's nothing different, but let's focus on these 3 components. So this is the 0th component, this is the first component, this is the second component, this is the third component. That's how we index them. So if we talk about first component, so first component, that is this gamma u prime fx prime will be equal to this row multiplied by this whole column. So we have gamma u prime fx prime is equal to, we have and just to distinguish between the gamma for the particle and gamma for the frame transformation, let us give this gamma subscript v. So with that we can distinguish that we are actually talking about transforming from one frame to other, where this is S frame, this is S prime frame. These two are not the same gammas. So we can write this thing now as we have minus gamma beta minus gamma v beta and gamma u by c dE by dt plus gamma v gamma u fx. Okay, this is the thing. Now gamma v is common, so we can take gamma v common. Also gamma u is common, So we can write this thing as fx minus 1 by c times beta dE by dt. Okay, and on this side we have gamma u prime fx prime. So your fx prime becomes gamma v gamma u divided by gamma u prime multiplied by fx minus 1 by c beta dE by dt. Okay, now gamma we know what it is, and gamma u by gamma u prime, this can be reduced to something else because we know the relation of the proper time. So proper time differential can be written as, in S prime frame the coordinate time differential is dt and gamma for the particle is u. In S prime frame coordinate time differential is dt prime and gamma for the particle is gamma u prime. So from here we can find that gamma u by gamma u dash is actually dt by dt prime. So we substitute this thing here, which gives us fx prime is equal to gamma v dt by dt prime fx minus beta by c d by dt. Now this dt prime you can find from the Lorentz transformation equation. So dt prime was your basically gamma v times t minus vx by c square, right? So your dt prime will be gamma v times dt minus v dx by c square, right? So we can now write fx prime as gamma v dt by gamma v dt minus v dx by c square times fx minus beta by c d by dt. Now if you divide by dt in the numerator and denominator both and cancel gamma v, then we will have 1 by v 1 minus v dx by dt 1 by c square fx minus beta by c d by dt. Dx by dt is nothing but ux, which is x component of the particle's velocity with respect to S frame, and we have fx minus beta by c dE by dt. So finally the expression of fx prime in terms of fx comes out to be this. We can box it, but there is more simplification we can do by rewriting this d by dt term. So dE by dt, we know that E is the total energy, which can be written as the rest energy m naught c square plus the kinetic energy, right? This is the total energy. So this can be expanded as d by dt of m naught c square plus d by dt of kinetic energy. We know that m naught c square is constant, so this will be 0, and this will be simply d ke by dt. Now by work energy theorem, which is also valid in the relativistic arena, we know that this dke is nothing but the work done, infinitesimal work done on the particle f dot dr. So this thing we can write as d by dt of f dot dr. This comes from the work energy theorem, now which can be written as f dot dr by dt, and this dr by dt is nothing but the velocity u of the particle with respect to frame s. So this is f dot u. So finally de by dt comes out to be f dot u. So if we substitute this thing there, then we find that fx prime comes out to be fx minus beta by c, which is basically v by c square times f dot u, and all divided by 1 minus ux v by c square. So this is the transformation equation that we have for the x component of the force. Now for the y component of the force, you can simply do this matrix multiplication. So for y component of the force, we will get gamma u prime fy prime is equal to this, and this will be 0, this and this will be 0, only this and this will give a finite term. So we get for the second component, we get gamma u prime fy prime is equal to gamma u fy. Okay, so your fy prime is gamma u by gamma u prime fy, and we know that gamma u by gamma u prime is dt by dt prime. So this is your dt by dt prime fy, and this thing we know comes out to be gamma v. So let's write dt prime. So dt prime comes out to be gamma v dt minus dx v by c square. Now divide by dt. So we get fy times gamma v 1 minus ux v by c square. So this comes out to be fy prime is equal to fy under root 1 minus v square by c square 1 minus ux v by c square. So this is the transformation relation. for the y component. And similarly for the z component, the transformation relation comes out to be f of z prime is equal to fz 1 minus v square by c square divided by 1 minus ux v by c square. This is what we get. So these are the three transformation relation for the forces that we get. If we were to collect it at one place, then we can write it as, let's collect it at one place. So this is the transformation relation for x component. This is the transformation relation for x component, and for y component, this is the transformation relation. And for z component, this is the transformation relation. So here we have transformation relation for all the components of the force. So if we have a force on a particle, vector f, with respect to one frame, then seen from some other frame s prime, the force will not be the same vector, it will be some f prime vector. And if you know f in S, then you can find f prime vector in S dash frame using these relations.